Hi all. In the last class we have seen cycles, definition of cycle, then length of the cycle, representations of the cycles. So if we consider a sigma, a cycle is equal to 1 to 4 in S5. So this is a cycle. So this representation of this notation represents the permutation 1, 2, 3, 4, 5 in S5, and 1 goes to 2 and 2 goes to 4 and 4 goes to 1. That is the meaning of this symbol, and other two symbols are fixed, that is 3 and 5 are fixed. So if you consider this S5, this element in S5 and another permutation or another cycle in S5 this another cycle contains the symbols 1 or 2, 3, 5. So this is the other cycle in S5. So we write this gamma as 1, 2, 3, 4, 5. 1 goes to 1 because there is no 1 in this symbols, and 2 goes to 3. 3 goes to 5 and 5 goes to 2 again. So the other two symbols 1 and 4 are fixed. Now if you consider the sigma, generally the sigma gamma need not equal to gamma sigma, okay, because we know that if you observe the image of 2 in this gamma sigma, what is gamma sigma gamma of 2? Sigma gamma of 2 is sigma of gamma of 2. We know that sigma of what is gamma of 2? Gamma of 2 is 3, and 3 is fixed in sigma, so this is 3. Now you observed what is gamma sigma of 2? That is gamma of sigma of 2. What is sigma of 2? Sigma of 2 is 4. Then what is gamma 4? Gamma 4 is 4 here, so image of 2 in this product is 4 and image of 2 in this product is 3. So which shows that these two functions are not equal. Okay, that means gamma sigma and sigma gamma are not the same one. Okay, but if you consider the cycles, if you consider the cycles in S5 which are disjoint. What do you mean by disjoint cycles? Disjoint cycles means that those two cycles contains no common element in that cycle representation. That means if you have another sigma 1 that is equal to 3, 4, 2 in S5, and gamma 1 as some 1, this is the cycle here, and we have 1, 5. This is another cycle in S5. So if we consider these two cycles, we can, sorry, this is in S5, so I put 5 here. These two are another cycles in another two cycles in S5. So if we consider these two cycles, we consider that sigma 1 and gamma 1 have no symbols in common. Okay, this is 3, 4, 2. There is no 1 here, 5 here, and similarly this representation, this notation contains no elements of the sigma 1. Okay, so if you consider two such cycles, these cycles are called disjoint cycles. Okay, if you consider this these two disjoint cycles, sigma 1 gamma 1, then observe sigma 1 gamma 1. So how will you find the product of sigma 1 gamma 1? First of all, write sigma 1, 1, 2, 3, 4, 5. In sigma 1, 3 is mapped to 4, then and 4 is mapped to 2, and 2 is mapped to 3. Then other symbols are fixed. So this is sigma 1, and you write gamma 1. What is gamma 1? 1, 2, 3, 4, 5. In order to get gamma 1, you need to interchange 1 and 5. So 1 goes to 5, 5 goes to 1, and other symbols are fixed. Okay, if you consider this product, so that will give an element in S5 itself, 1, 2, 3, 4, 5. Then how will you find the product? 1 goes to 5 and 5 goes to 5. So image of 1 is 5, and image of 2 is 2 goes to 2, 2 goes to 3, and image of 3 is 3 goes to 3, 3 goes to 4, and image of 4 is 4 goes to 4 here, 4 goes to 2 here, and image of 5 goes to 1 and 1 goes to 1. So this is the product sigma 1 gamma 1. Similarly, if you find the product of gamma 1 sigma 1 by interchanging these two permutations, you will get this product 1 2 3. This is our gamma 1 and this is our sigma 1. Then you will get the same permutation 1 2 3 4 5. This is 1 goes to 1 here and 1 goes to 5 here, and 2 goes to 3, 3 goes to 3, so we have 3 here, 3 goes to 4 here and 4 goes to 4 here, and 4 goes to 2 here and 2 goes to 2, and 5 goes to 5 and 5 goes to 1. So if you consider this two disjoint cycles, then you can say that sigma 1 gamma 1 is same as gamma 1 sigma 1. That means these two disjoint permutations commute. Okay, that means if you consider, if you since that is because of this reason, if you consider sigma 1 gamma 1 this product, then the change in this the change for the symbol 1 in this is 5, and that 5 can act as identity the effect of this 5 in this sigma 1 as the same as the identity permutation. Okay, that means this if you consider this permutation, these symbols are fixed. Okay, so if you consider the images of and similarly if you consider this permutation 1 and 5 are fixed. So if you consider the image of 1 in this product, then there is only one action for this 1 in that is in this permutation. So and that symbol 5 is fixed in this permutation. Okay, there is no effect or there is no change in the symbols for the symbols 1 and 5 in this permutation. So if you consider the image of 1 and 5 in this product, this can act as identity for the symbols 1 and 5. Okay, if you want to find the images of 2 3 4 in this product, this can act as identity for these symbols. So that's why we can get the commutativity for the disjoint cycles. Okay, so there is a famous result. This is an interesting result. Disjoint cycles commute. Cycles commute in Sn. If you consider any Sn, if two permutations are cycles which are disjoint, then that commute. Okay, that means sigma 1 gamma 1 is same as gamma 1 sigma 1. And another interesting fact on this cycle is if you consider sigma as the cycle 1 3 4 in S4, so you can write the sigma as 1 3 4. That 1 3 4 is nothing but how will you extract that permutation 1 2 3 4, and this 1 goes to 3, 3 goes to 4, and 4 goes to 1. 2 is fixed. So this is the permutation in S4. And if you consider the other cycle 3 4 1, what is the representation, what is the form of the sigma in S4? Okay, if you have or sigma, suppose this is sigma 1 and I write sigma 2 as this, what is sigma 2? Sigma 2 gives 1 2 3 4. That is 1 goes to here. If you observe this notation, then the image of 1 is 3, so 3 here, and image of 3 is 4, so here you have 4, and image of 4 is 1 again, so this is 1 and this 2. This shows that 1 3 4 is same as 3 4 1. That means these two notations represent the same cycle in S4. Okay, so similarly if you write sigma 3 is equal to 4 1 3, so that will give the same permutation 1 2 3 4. From this you can say that image of 4 is 1, image of 1 is 3, image of 3 is 4. Okay, so that will give the same permutation as well in S4. Okay, so that means the cycle notation or this represents, if you consider this 1 3 4, that can also be represented using 3 4 1. So that is also same as 4 1 3. Clear? That means a particular cycle in S4 or any Sn has more than one representations. Okay, so if you consider this cycle 1 8 6 7 5 in S10, okay, then the same cycle can be represented using the symbol 86751. Okay, similarly this can be written as 67518. Okay, that means if this has since this is a cycle of length 5, then you can get the 5 same representation, the 5 different representation for the same cycle. Okay, so a cycle can be written in more than one way. If a 5 cycle can be written can be represented in 5 different ways. Okay, so please note that these three cycle permutations are the same. Okay, similarly this has 5 representations: 7 5 1 8 6, and another one more is 5 1 8 6 7. Okay, so these 5 representations, or these 5 notations, represent the same permutation 1 8 6 7 5 in S10. Okay, so there are more than one representation for the same cycle in Sn. Now we consider permutations which are not cycles: 1 2 3 4 5 6, and this is 4 5 1, and this is 6 2 3 is fixed. So if we consider the sigma, then we can say that using the orbits, here the orbits are 1 4, 1 goes to 4, 4 goes to 5, 5 goes to 1, so this completes one orbit. And starting from 2 2 6 is another orbit, and the third orbit is 3. Okay, so these 3 are the orbits of sigma. So if you using these orbits, we can represent this as the product of cycles. Okay, so we write this is 1 4 5, this is a cycle. 2 6, this is another cycle, and 3 is the cycle of length 1, that is identity, so that we need not write that identity here. So you can avoid, or you can remove all the cycle of length 1, so or orbit containing one element. Okay, so using the other orbits, you can represent the sigma as a product of disjoint cycles. Clear? So if you consider this is some b1 and this is b2, b1 is corresponds to this orbit, and b2 corresponds to this orbit. Okay, so if you write sigma as a permutation in S6, then that sigma can be written as product of these two cycles, disjoint cycles. This 1 4 5 represents a permutation in S6. Similarly 1 4 5 similarly 2 6 can represent a permutation in S6 as well. That means 1 2 3 4 5 6. This 1 4 5 represents 1 goes to 4, 4 goes to 5, 5 goes to 1, 2 3 6 are fixed in this b1. Okay, similarly 1 2 3 4 5 6, and here 2 goes to 6 and 6 goes to 2. The other symbols are fixed in b2. Okay, that is the meaning of this cycle. Okay, 4 5. So if you take the product of this, you can get sigma. Okay, that means sigma can be written as a product of disjoint cycles of the form b1 and b2. Okay, so have you understand this? If you have in order to find sigma of 1, you just find the image of 1 in b1. Okay, that is if this is b1, then b1 of 1, this will be the same. Okay, so similarly because that 1 is in this cycle notation. Okay, in order to get sigma of 2, you write this 2 is in this b2, then you write b2 of 2. In order to get image of 3, 3 is not in neither in b1 nor in b2, so for sigma of 3 is 3 as it is. Okay, in order to get sigma of 4, how will you get sigma of 4? You just find 4 comes under this orbit, or 4 is in b1, then that will give b1 of 4. b1 of 4 is the image of 4 in this b1 is 5, so that is same as 4 5. Okay, just observe that how to get sigma of 6. Sigma of 5 first, then 6. Sigma of 5. In order to get sigma of 5, just observe 5 is in b1, then b1 of 5 is same as sigma 1 of 5. Similarly, sigma of 6. Sigma of 6 in the second cycle, then b2 of 6 is same as sigma of 6. So this proves that sigma is same as b1 and b2. That means if you collect the symbols 1, 2, 4, 5, 6, these are the symbols which undergoes the changes. Okay, so if 1, 2, 4, 5, 6, any one of these symbols 1, 2, 4, 5, 6 are in b1 or b2, then we write for those symbols we write sigma of 1, sigma of 2, sigma of 4, sigma of 5, sigma of 6. Okay, if there is a symbol 3 which neither in b1 nor in b2, then we take the image of sigma of image of 3 as 3 itself. Okay, so for all other symbols we consider sigma of 3 as 3. Okay, so if you define such a define such cycles, then that if you define mu1, what is mu1? Mu1 is defined as, if you find the image of, this is our mu1, so I put this instead of b1 I write mu1 here, and this is mu2. So how will you define this mu1 and mu2? Okay, so in order to define mu1, you first observe that 1. Okay, if this one is in if this one, we know that this one is in b1, so you write mu1 is nothing but sigma of 1. Okay, and take 2 is in b2, then this is sigma of 2. Okay, sorry, this 2 is in b2, so this is not in b1. That means we know sigma 2 is in b2, so you write, in order to write the image like this, in order to write the image of 2, you first observe 2 is in b2, that means 2 does not belong to b1. If 2 is not in b1, you write the image of this 2 is 2 itself. Okay, so that is, this is mu of 2 is equal to, we write mu of 2 is equal to 2 itself. Otherwise mu of 1 is equal to this one. Right, this is mu of 1 is equal to define this mu1 of, this is mu1 of 1 is equal to sigma of 1, since this 1 belongs to b1. Okay, so mu of 2 is equal to 2 because 2 does not belong to b1. Now observe 3. We know that 3 does not belong to b1. If 3 is not an element of b1, you define mu1 of 3 is equal to 3. Okay, and if you observe 4 is in b1, 4 belongs to b1, then mu1 of 4 is equal to, that is same as sigma of 4. Okay, 5 is again in b1, then mu1 of 5 is equal to sigma of 5. And 6 does not belong to b1 because 6 is in b2, so 6 does not belong to b1, then you write mu1 of 6 equal to 6. So mu1 fixes the elements 2, 3, 6. That means this fixes the elements 2, 3 and 6. So this defines the first cycle. Then how will you define the second cycle? In order to define mu2, how will you find out mu2 of 1? So first observe 1. This 1 is an element of b1, therefore 1 is not in b2. Okay, if 1 is not in b2, then image of 1 should be 1. Okay, mu2 of 2, how will you get mu2 of 2? First observe 2 is an element of b2 or not. 2 is an element of b2, that means 2 is an element of this orbit, then you can take the image of 2 as sigma of 2. Okay, 3 not in b2, So mu2 of 3 is same as 3. Now 4 does not belong to B2, then we can say that mu2 of 4 is this is not in B2, then you can fix it. Okay, so if you define this mu2, you observe these symbols. Okay, 1, 3 and 1, 3, 4 and 5. These symbols are not in B2, therefore the images of those symbols are the same. And if you consider 2 and 6, that is those symbols are from B2, that is the second orbit, then you consider the image of 2 as same as image of 2 in sigma. Okay, that is 6 and 6 goes to 2. So this defines mu1 and mu2. So once you get sigma, then using the images of or using the orbits of this sigma, you can easily define you can easily define disjoint permutations whose product will give this sigma. Okay, so this defines the important theorem which we have mentioned yesterday. That means any permutation can be written as, any permutation in Sn can be written as product of disjoint cycles. So now we can see the definition, we can see the statement. This is the statement: every permutation sigma of a finite set is a product of disjoint cycles. So first we start with a permutation that sigma belongs to Sn. So corresponding to the sigma, we define disjoint cycles. Before that, we consider sigma as a orbits. Let B1, B2, etc. Br are the orbits of sigma. Okay, now you define mu I. How will you define mu I? In order to define mu I, you consider the symbol, or you consider any symbol if x belongs to this Bi. Corresponding to each orbit, we define this mu I. Okay, if x belongs to Bi, then you define image of this x under this mu I is sigma of x. Okay, if x is not in Bi, then when you write this sig mu I, that x should be fixed, so image should be x itself. Okay, so we can see that this sigma is equal to mu1, mu2, etc. mu r. Okay, so how will you prove this? In order to prove this one, you need to write, we need to get sigma of x equal to mu1, mu2, etc. mu r of x for all x. Okay, so first you write x belongs to 1, 2, 3, etc. n. Okay, then we know that x belongs to one of these orbits, x belongs to some Bi. Then we can say that this mu I of x equal to sigma of x. Okay, all other symbols are fixed. Okay, so we can easily say that if x belongs to Bi, then mu I of x equal to sigma of x. Now consider the right hand side. What is mu1, mu2, etc. mu r of x? Okay, we know that x belongs to Bi, therefore this mu1, mu2, etc. mu r of x. Okay, this is same as mu r of x equal to x, because x belongs to Bi, therefore these b1, b2, etc. br form a partition. So if x belongs to Bi, means x does not belong to other elements in that other sets. So mu r of x. Okay, so from this since this x does not belong to Br, you can set mu r of x equal to x itself. So this will be mu1, mu2, etc. mu I, etc. mu r minus 1 of x. Okay, similarly you can write this the same as mu1, mu2, etc. mu I of x. Okay, so we know that this is sigma of x, mu I of x equal to sigma of x, because x belongs to Bi. So that is mu1, etc. mu2, etc. sorry, mu1, mu2, etc. mu I minus 1, mu I minus 1 of sigma of x. We know that sigma of x, this x belongs to bi, then sigma of x is also in bi, so that is an orbit. So this will give again, repeating this, you can get this is equal to sigma of x. So which shows that this of x is equal to sigma of x. Clear? So which shows that this mu is equal to, sorry, the sigma is equal to mu1, mu2, etc., mu r. That is a product of disjoint cycles. So this proves this theorem. Now you need to explore some examples given in the textbook after this theorem. So please go through it and please come up with your doubts. Thank you.